example number 37 of the book authored by Logan. So it's number 7, chapter 3. As you see, there is a truss structure consisting of 2 bar elements, and there is also a sort of spring connected to node number 1. And we have an external force 25 kilonewton applied vertically on node 1. And the characteristics for truss elements, those 2 elements are the same, identical, and we have the module of elasticity and the section area, as you see. And one of the elements is 5 meter and the other is 10 meter. And you need to solve the geometry and to be able to model the structure. You need to solve the geometry to be able to define your grid system. So if you have 45 degrees here for this triangle here, I have solved this, and you can see this distance and this distance will be equal to 3 meter and 54 centimeter. This is very easily can be achieved by writing the definition of cosine of 45 degrees and sine of 45 degrees. And you have this element length equal to 5 meter. So just I put these definitions aside just to be able to take the numbers there. I go to the E tabs, starting with a fresh model, and I follow the matrix SI system. For this example, I press OK. I need in the X direction, I need 3 grid system, and then Y direction 2. In the X direction, it's not equally distanced. So this is not something I want. I will go to custom grid spacing and edit it. So in the X direction, A is 0 and B is 6.46 meter and C is 10 meter. And in the Y direction, I really don't need anything but the first one. I press OK. And for the stories, I need only 1 story, and the height should be 3.54. And I just use grid only and press OK. So again, I like to work in the XZ 2D plane system. I just go to the elevation number 1, and here we are. So yeah, I just go to create my bar elements first. I grab this one and this one. This is the second element actually. And I grab this one and this one. So I have exactly those 5 meters and 10 meters elements here. So this node and this node, they are fixed. I just go and fix them. They don't move anymore. And I just go to define the material property. I can modify this one, name it like my material, and I set the density equal to 0 because I don't want any self load to be added to the system. So the module of elasticity is 210 gigapascal, which means 1, 2, 3, a megapascal. So 210. Yeah, these 3 zeros are added here just to transform the gigapascal to megapascal. All right. So this is my material. I press OK and define section property, and I add a new property like a general section here. Press OK. So this is my element. Material is my material, and we have 5 square centimeter for the section area. So it's 5, 5, 5. And that's okay. This is my element. I just grab these 2 elements and assign, because so far I just defined those characteristics. I need to assign them to my elements. So I just go to frame section property and assign the my element to really my elements. So as you see, they are assigned to my element characteristics. Again, I grab those 2, I assign them to no, the frame, sorry, here, the frame release and partial fixity. I need to end release them just to model they have 2 hinges at both sides. So now they are truss elements, I would say. So these 2 are fixed, but this node should be free. I just assign this to restraint. This is fixed, okay? But this should be free. And X, translational X, translational Y, translational Z, and rotational Y. These 3 are released to be able to move. However, I don't release the others. The others are out of plane. So because I'm working in XZ 2D plane system, the others, for example, the translational Y is out of plane, and those 2 rotational X and Z are out of plane, which I just keep them closed. So I just press OK. I have an external force here, so I just grab this one. I assign joint load force, and the force is 25 kilonewton vertically, so it should be here, and it should be minus 25 kilonewton because it's vertically from top to bottom, and my z-axis is here. From bottom to top is positive, from top to bottom is negative. So I just put minus 25, which means if I press OK, you will see it's from upside down. And I need to define a spring here as well. So I just grab it again. I just go to assign joint a spring. Can you see this? I can simply define a spring in that node. So I just define a spring, add new property. I can name it whatever you like, my spring. And the spring constant should be vertically defined, which means in Z direction. It is 2000 kilonewton per meter. So here I have kilonewton per meter, so it should be 2000. Spring constant is always positive, and this is simple spring stiffness in global direction. Okay. Now press OK. Now press OK. I assign my spring to this node and press OK. You can see there is a spring here. If you right click on the node, you will see you have a spring here. Oh, sorry, I just changed it. Sorry, I made a mess. I just cancel it. Again, I right click on it. See, a spring is here. You can change it here, but I just keep it as my spring. Okay. I think we are ready to run our model. Just save it, example 3.7, and it will take a couple of seconds to be run. And so that's fine. Done. I just go to the left-hand side window and I want to see the deformed shape of the structure, like in dead loads. Okay. So as you can see, it's going down left. I just make it a little bit smaller just to be able to read those numbers. Right click on this one and you can see, sorry. If you right click here, you can see these numbers. And if you on the right hand side window, the 3D one, if you right click on it, you will see this pop-up window, which shows the translational displacement is minus 1.72 millimeter. Millimeter is here. And in Z direction, the vertical one is minus 3.45 millimeter. And as you can see, they are absolutely the same as what you got from the hand calculations during the slides. And it means that everything is correct in hand calculation and here. And as you know, you can check the internal forces or support reactions. Everything is here in display menu. You can see forces in supports here or in the elements here. In the support reactions, you should say, show me Fx and Fz and press OK. These are the support reactions. You can check them with the hand calculation results and you will find they are absolutely identical. And if you go again on display menu, and this time frame, pier, spandrel, link, forces, it means frame forces. And for the frame forces, you should go for dead load and axial force. You need axial force, you don't have anything else. If you press OK, you will see these are the axial forces, which is constant, of course, along the element. So this red means it's compression, the yellow means it's tension, it's 25, it's minus 18. And for example, if you really go for frame forces and you say, okay, show me the moment and press OK, you see it's zero. So it means that this is a truss structure and you don't have any moment or shear forces along the elements. So feel free to more elaborate with your model in other ways to better understand the behavior of it or change the external force or the spring constant or whatever you like, and just try to better understand the behavior of ETABS in modeling different truss structures. Thank you for watching this video.